Okay, so welcome everybody to Project Open Secure, which is a RISC-V secure ML system framework. My name is Kai. I'm from Google, within the Google Research Organization. And in today's agenda, we will go through a high-level overview of our project, our partners, and our plan for 2024. Last year, we introduced system code development for RISC-V with Project Sparrow and Renode. And together with Michael from Antmicro, we presented a high-level overview of the system code design process, the infrastructure and tools, as well as the exploratory OS that we call Cantrip, and enhancements that we also made to support RISC-V in both our infrastructure tools as well as Renode. We articulated our goals for 2023, and I'm not quite sure who remembers, but we have essentially reached most of the milestones that we have set forth this year. And we're at a point where we're ready to develop a lot of the stuff that we have been putting together in open. Of course, we'll go over in details in just a moment. And we have adapted a new name as well called Project Open Secure, obviously previously called Sparrow. Project Open Secure is an open source toolkit and infrastructure that facilitates the collaborative design of secure, scalable, and efficient RISC-V systems. Our mission is to empower the creation of innovative applications, streamline the code design development process, and promote transparency and auditability. Our code design process encompasses a system architecture generation block equipped with a parameterizable set of RISC-V IP library, behavior simulation, RTL simulation, as well as physical design simulation. Each phase within the iterative design process delivers a distinct level of feedback, ranging from coarse to fine. This approach emphasizes on rapid feedback from the tooling to facilitate quick failure detection and early correction through our design flow and process. With that said, I'm going to pass it over to Cindy, who's our lead engineer, to go over some of the highlights.
Thank you, Kai. Can everyone hear me? Okay, thanks. So in the previous slide, we have shown a chain of tools allow us to design and optimize the machine learning system iteratively. To start with, we have composed and configured the system using hardware JSON description. Passing through open source tools like FuseSock and Idealize, we can build the system for different hardware targets. Afterwards, the design can be verified in its performance, first in system simulation in Renode, then in RTL simulation in VeriSilicon. To build the system, we also provide a hardware IP library. Within it, there are 3 RISC-V-based processing cores. System management core interact directly with the user application. It has MMU, supervisor mode, atomic extension support, in order to run secure operating systems such as Cantrip OS, followed by a low-risk hardware root of trust. The third core is another RISC-V-based ML core with custom instruction in order to deploy machine learning workload more efficiently. The other IPs, such as TileLink, peripherals, and the vision processing, are also included in this library. In terms of generating the machine learning workload, there are 2 frameworks supported. First is the TensorFlow Lite for microcontroller. It takes machine learning model using TF-Lite format as an input, following an interpreter kernel framework to generate the workload. The other one uses ERI, a MLIR-based machine learning deployment framework that optimizes the machine learning workload in compilation time. It also supports different machine learning input format. Both flows are backed by RISC-V GNU toolchain, modified to support the custom instruction we just talked about, and to generate the final software workload. Following this flow, we have built a reference design to demonstrate a secure, low-power system for machine learning applications. The system, including the hardware design and the software design, are first verified using system simulation in Renode, as well as FPGA emulation. We're working with VeriSilicon on IP validation and the silicon realization, targeted to be available in early 2024.
All right, thank you, Cindy. Okay, by forging strategic partnerships with both university, low-risk foundation on obviously it's a secure root of trust, VeriSilicon and Antmicro, we aim to accelerate the project's development and infuse our research development outcome into the ecosystem. These collaborations enable us to bring the best that each of the companies have in terms of domain experience and expertise, and bolster open secures, tooling, and infrastructure. This in turn enables us to innovate, accelerate, and address the risk associated with adoption for Google's ecosystem of products in the future. So, having that said, I'm going to kind of pass it to Michael and Antmicro to talk about his experiences with OpenSecure in the collaboration.
Thanks, Kai. Right, so we're extremely happy to have collaborated with Google on this project. And one of the reasons is that OpenSecure actually fits the theme of everything we do very, very well. So basically, our company helps customers build products in a vertically integrated way. Everything we do aims for a more software-driven, a more productive methodology of working to roll out products into markets quickly, especially for RISC-V, of course, which is an exciting opportunity to customize everything. And so we work on different levels of the stack. We work with hardware boards, we work with software, we build BSPs, we maintain Zephyr for RISC-V, we build machine learning solutions, up to cloud, OTA, and fleet management solutions. So having an open source machine learning accelerator like OpenSecure suddenly also gives us the ability to innovate on the hardware level, to actually customize the entire flow throughout, from hardware up to the cloud. So this is really, really exciting. And this also kind of fits a broader ecosystem. So OpenSecure joins a number of tools that we're working on, and these are both internal ones like Renode that we're talking about today, which is an open source simulator, but also our suite of OTA frameworks like RDFM, our AI library Kenning, as well as tools that are of course not coming from Antmicro, but we nevertheless contributed them heavily, including, for example, Verilator for HDL simulation, including the Zephyr RTOS, where we maintain the RISC-V port, or systems like Linux, Android, Talk, and so on. So overall, this entire ecosystem of open source components works together pretty well, because of course, open source makes it super easy to integrate things together and reuse across a number of different solutions. And specifically as part of the project, we've been developing a lot of things in Renode. So it's both that Renode benefited the project in terms of enabling a whole software-driven methodology for co-design, but so has the project benefited Renode in helping us develop a bunch of functionalities. Predominantly, of course, a lot of the work has been done in enabling the support for the hardware. So obviously, this is based on OpenTitan. We have support for the majority of the peripherals there. We have support for RISC-V naturally. We extended support for RISC-V vector extensions. I mean, we covered the entire 1.0 spec. We've also worked a lot with custom instructions, with heterogeneous setups for simulating, multi-core heterogeneous SOCs. And overall, it's been a blessing to the framework, enabling us to work on so many levels, improving RISC-V support throughout. Another area that's seen a lot of active work thanks to the OpenSecure project is tracing. We've done a lot of work on enabling better tracing, data gathering for the analysis of performance, for allowing you to do machine learning co-development where we have all the data that you need to realize what the trade-offs should be. One of the things that we're excited about as well is the ability to also include microarchitectural data, like fusing this with whatever data you get directly from Renode with another tool called TBM, where we can kind of get a more precise performance data so that we can do even more informed choices about those trade-offs. And generally speaking, if you look at the broader picture, the reason why this is exciting with Renode is that we can also do sensor simulation. We can do end-to-end, machine learning scenarios with data ingestion using a format that we designed called REST, up to the actuators. So we can do an entire machine learning flow completely in simulation with the binary exact same software that would run in production, all in simulation. Summing up, I mean, we're excited to be looking at future customer projects where we're going to integrate Cura into people's solutions. We do that today all the time, except that we mostly use proprietary AI solutions. And this isn't ideal in the sense that, you know, you can only optimize so much. Much of the flows and libraries in the AI space close to hardware are actually very often closed as well, right? So Cura is extremely good in terms of making your RTL available, making the entire flow, including the AI libraries, also open source. So you can really optimize down to the metal. And yeah, this makes for a really exciting promise for the future. With that, I'll leave it to Chris at VeriSilicon.
So I will talk about the collaboration between VeriSilicon and Google on the reference SOC design for this Cura project. First, a brief introduction of VeriSilicon. VeriSilicon provides a rich IP portfolio around the pixel processing pipeline. Based on these IPs, we build a platform to provide chipset design service for our customers. We tape out 30 to 40 chips annually today. We call ourselves a SiPaaS company, which means Silicon Platform as a Design Service. So these are the pixel processing IPs that we are offering today. We have ISP IP, we have a video codec, we have an NPU, we have a GPU, we have a DSP and DPU, ranging from camera in all the way to display out. So for all these IPs are scalable, and also we provide automotive-grade designs for all these IPs. So in the Cura reference design, we have our ISP IP, video encoder, audio DSP, MIPI IP, and the power measurement IPs inside. So the SOC design is about to be done. By working together with the support of Google team, we have completed a chip-level architecture design, SOC integration and verification, physical implementation, FPGA emulation, and verification. We also measure the chip tape-out flow, including package design and dry run. So here are the key milestones for the design. The open source version of the ISP IP was just released together with the whole project. So the MPW tape-out will be next month. The reference board will come back roughly by the end of Q1 next year. So here we want to extend our special thanks to Google team for their dedicated effort and support in the past 2 years. It has been a pleasure to work with you guys. So now let's talk about the applications of the Cura design. So when we design the SOC, 3 major factors have been taken into consideration. First, it is secured. It means the data is protected. Secondly, it's low power, which enables edge processing or always-on solution. Last, so as its artificial intelligence comes naturally as Google's machine learning Kelvin core is inside. So by working together with Google team, we are deploying some reference demos, some demos on the reference board. The demos includes human presence sensing, motion detection, audio tokenization, voice wake up, voice command, and audio-based noise reduction. Potentially, there will be more applications. So if you are interested in leveraging the reference design, so we will be very pleased to work with you to explore how to leverage the current achievements today. The whole output of the design can be applied for commercial usage. It can be slightly customized to meet your specific requirements. So for more information, please contact VeriSilicon or Google team. So the evaluation boards will be available, as said, Q1 next year. So please contact our sales for the evaluation boards. The reference boards will be distributed by our partners later on. So this pretty much concludes my part. Thank you.
Yeah.
Thanks, Kai.
All right. Oh, it's okay. You can hang on. All right. Thank you so much. Got it. Appreciate it. So moving on to learnings. There's so much learnings, but to quickly summarize, I want to articulate that RISC-V Open ISA and availability of open source tooling and infrastructure and a vibrant community enable us to put together a configurable framework that allows us to do code design and development and exploration. I think the openness, extendability of the architecture truly enable us to do hardware, software code design in a full stack configuration, right? Because oftentimes proprietary IPs are essentially black box on the bottom. So it also enables us to essentially put together that reference design that you saw earlier today, right? Allowing us, reaching to a point where we could iterate very rapidly, generate more in the future. So, however, maybe the maturity and capability of some of the tools that support RISC-V are still ever evolving. So one of the things that we did not anticipate as much was that we have to put additional resources to make sure that we keep up to pace with the evolution of the tooling, right? And the changes that are coming in. So that is one caveat that I would probably mention. But other than that, let's go toward the goals of 2024, so we have some questions. So with the goal for 2024, we plan to continue to improve the tool and infrastructure through each of our design phases internally. As we take that feedback in, we want to come out with better ways and improvements in the tool and infrastructure so we could co-design much quicker and faster, right? And on top of that, we want to validate the system that we have co-designed together today as a test chip, as well as getting that feedback back into our tooling. And we also want to explore new system design that enable new use cases as well. Obviously, beside reference systems and designs, we also want to evolve the core technology. We're working with both industrial partners as well as universities to explore both maybe Calyptra as a future root of trust, as well as evolving the ML capabilities and technology. One that is more closely with how we see ML evolve internally in terms of model architecture and design. And on top of that, we really want to put some focus in Cherry capabilities and Cherry enablement into our system design as well over time for memory safety and other isolation capabilities. Having all that said, I mean, the most important thing is, where's the source, right? So the source is available now at opensecure.googlesource.com. We plan to do a deeper dive at the CHIPS Alliance workshop on November 9th between 9 and 10 a.m. So I'd love to welcome everybody to participate. Do we have some time for questions? Yeah. Yay. Oh, yay, okay, questions. And Cindy will come answer questions.
Any questions? We have 3 minutes for questions, so anyone? Here.
For the root of trust, is there any particular reason to use open source RISC-V for the RT IPs?
So first of all, one of the reasons why we use open source IPs or designs is that we can open up the design for the general public for the validation and verification. So that's the reason why we choose the open source version versus other existing IPs. And the Open Titan is one of our collaborators that we adopted the low risk hardware root of trust. And just like Kai just mentioned, there are other open source resources or libraries that we are considered for the future involvement or the iteration of the design. And we are happy to collaborate with anyone. And we believe that the open collaboration is really the way to make sure that our whole system is secure and gain the public trust out of it.
Yeah, trust is very important, as well as the ability to audit the code, and the hardware that runs on.
More question? We have time for one more question.
Hey there, thanks for the interesting presentation. Again, on the root of trust, I'm just wondering if you could talk a bit about why you're looking at moving to Calyptra as a root of trust.
The Calyptra?
Yes.
Yeah, right now we are in the early engagement stage. We haven't decided yet. That's one of the paths that we are exploring. And the Calyptra is another open source project that we are currently engaged on. We are, like I said, in the early phase, and we are going to make the exploration being visible in our code base. Whatever that we do or the design choice that we make, you will be able to see that in our change history.
Okay, thank you.
The good, the bad, and the ugly.
So
Hopefully not ugly.
we do not have more time for questions, so thank you
Okay,
very much.
thank
for
you so
your
much. I
presentation.
appreciate it.